So before we continue with where we stopped last time, let's just do a quick recap of what an inner product is. Okay, so we went through all the stuff last time. So an inner product space, or sometimes called an IPS, inner product space, we saw that it's just a vector space over the real numbers, and I told you all sometimes this could be over the complex numbers. It doesn't always need to be the real numbers. So it's a vector space with a special type of function. Okay, and this function we denote it by this symbol, and this function takes in two vectors from your space and it gives you a number. Okay, so it takes in two vectors and gives you a number, but it also needs to satisfy a couple conditions. And the first condition is if you put the same vector, so you can think of it like a machine, right? So this is your inner product, and it takes in two vectors, and it gives you a number. If you put in the same vector with itself, it should give you a non-negative number. If you put in the same vector with itself and it gives you 0, that only happens if and only if that vector is a 0 vector. Okay, so that's the second property. The third one is symmetry, which means it doesn't matter which you put in the first component or which you put in the second component. So inner product of U with V is the same thing with inner product of V with U. I had mentioned that if you're reading this in a textbook, sometimes you may see they have this guy complex conjugate. So that is true, but that is if you're working over, if the inner product is over the complex numbers. Okay, but for us, we're going to stick to the real numbers, so we will have this symmetry property. No need to put the complex conjugate, because if it's a real number, what is the complex conjugate of a real number? It's the same number. And the last property is what we call linearity. So linearity is essentially the same thing, the same linear property that we saw when we were studying linear transformation. And it says that if you put in the first component a linear combination of vectors, for example, AU plus BV, you could essentially break this up into two inner products. Okay, and you could think of it like it's distributing. So AU, inner product of AU with W, and then you could pull the A out, and then it's the inner product of BV with W, and then you could pull the B out. Okay, and you could actually show that in this case, if we are taking inner products into the real numbers, it's not only linear in terms of this first component, but it's also linear in terms of the second component. And in this case, we just have a combination of two vectors, U and V, but it can handle any finite combination of vectors. So it doesn't have to be two vectors. It could, for example, be 10 vectors here, and the inner product will break up into 10 separate inner products. So it's just like what we saw with linear transformation. That's why it's called linearity property. Okay, and a space, a vector space V, together with an inner product is called an inner product space. Okay, so inner product space is a vector space with this special type of function. And we looked at last class a bunch of examples of these inner products. So I'll just skip through it. Yeah, so just to recap again, we also saw something called a normed linear or a normed vector space. So just like we have a inner product space, which is a vector space with an inner product, there's something called a normed vector space, which is a vector space with a norm. And again, you could think of this norm as being a machine. So the norm we denoted by two vertical lines on each side. And this norm machine, it takes in one vector. So the inner product takes in two vectors. The norm takes in one vector. And it gives you a number. Okay, so it gives you a number, a non-negative number, actually. And how do you get the norm? So if you have an inner product, this is the formula to get a norm. All you do is you take the inner product of the vector with itself and you square root that guy and you will get the norm of the vector. So you could, the interpretation of the norm is it's going to give you, or it's going to sort of measure the length of a vector. Now, remember back in high school where they told you that like a vector was, say, like, and they told you that a vector was an arrow or something like that, and they told you that this was a vector, and the magnitude was simply the length of this arrow, right? So this is the length of this vector, the magnitude. So this is true. But we're seeing in this course that not only are these arrows vectors, but there are many other objects that satisfies properties of being a vector. For example, a polynomial. Polynomials are vectors. So what does it mean to have the length or the magnitude of a polynomial? Okay, so this idea of a norm generalizes that whole notion of length, not only to arrows, but to anything, to any vector. Okay, so we can now measure the magnitude of function because functions are vectors. We can now measure the magnitude of polynomials. We can now measure the magnitude even of matrices because matrices are vectors. Okay, and again, it's give one way to do it is this formula here, square root of the inner product of whatever vector that is with itself. Okay, so that's a normed linear space. Right, and we looked at some special type of norm. One of them was called the Euclidean norm, which is just turns out to be the Pythagorean theorem in n dimensions. So the Euclidean norm is if we are measuring vectors in Rn. So again, the inner product in Rn is the usual dot or scalar product, you all know. So the norm of a vector in Rn is just the dot product of the vector with itself, and whatever number you get, you square root it. So this is what the formula would be. So if it was just 2, if we were in R squared, for example, if we were in R squared, we just have 2 components, right? So we wouldn't have this guy. So if we were in R squared, we just have the square root of x1 squared plus x2 squared, okay, which you know is Pythagoras' theorem. Yeah, so I think this is where we stopped on last time. Okay, so I said that the norm will allow us to measure the length of any abstract vector, not just vectors in Rn, but what if we are dealing with now polynomials? So let V be the space of all linear polynomials, and it doesn't need to be linear, by the way. It could be any sort of polynomials. But for this example, let's look at linear first. Defined on this interval, 0, 1, okay? And we're going to consider this inner product. So the inner product we saw we could put on these sort of spaces that have functions. One way we could define an inner product is we multiply these two functions together, and then we integrate that guy over over the domain. In this case, we take the domain as 0, 1. Okay, so if you work out this object, it will give you a number. So that's the inner product. Therefore, the norm is the inner product for f equal g. Okay, so if we set f equal g in this formula, we get this formula, which is the norm of this vector. So now we are assigning to a polynomial an idea of a length or a magnitude of this polynomial. Okay, and all you do is you just square the polynomial, so you'll know to square a polynomial and integrate that guy from 0 to 1, and whatever answer you get, you square root it. So for example, what if I give you the polynomial 1 minus 2x? Okay, what is the magnitude? What is the norm of this polynomial? So we just plug that equation into the formula. Okay, so we get the integral of 1 minus 2x squared. So expand it out. So you know it's a squared plus b squared plus 2ab. And integrate this. So you'll know to integrate polynomials and evaluate it from 0 to 1. And when you work out all of that, you get it is equal to 1/3, right? But we need to square root it. Okay, what we just worked out was this guy under the integral. We need to square root it. So therefore, the norm of this polynomial is the square root of 1/3, which is 1 over root 3. Okay. And we also saw if you have a vector u, you could convert this vector into something called a unit vector. We denote it by u hat. And all you do is you take the vector u and you divide by its norm. Okay. So in a similar way, we could convert this polynomial into a unit polynomial, a polynomial with length 1, and that's given by this guy, f hat. So all we do is we take the original polynomial f, and we divide by its length. So divide by 1 over square root 3. So if we divide by 1 over root 3, it's the same thing as multiplying by root 3. Okay, so this is the norm of f, or 1 over the norm of f. Right, so that's a polynomial of unit length. Yeah, so I put over here that this could be any type of continuous functions, not only linear polynomials. This will work for any sort of continuous functions, and the domain does not have to be from 0 to 1. So any continuous functions on any bounded domain, we can uh, do this sort of calculation and assign it a length or a magnitude. Okay, so at this point, I don't know the difference between an inner product and a dot product. So what is the difference? Let me ask you that. What is the difference between an inner product and a dot product? Anyone wants to take a shot at it? You could type it or you could unmute your mic and tell me and tell the class. Come on, don't be shy. So think about it while I pull up the next set of slides. Okay, so I see we have in the chat, a dot product is an example of an inner product. Yes, very good. Okay, so there are many, an inner product is something very general. It could apply to any function on a vector space that satisfies those 4 properties we looked at the beginning. So an inner product is a general sort of thing. So you can think of the inner product if you think about, let's say, like cars or something. So an inner product you could think of as a car. That's something very general. But then, there are different types of cars and different makes and different models, right? So a dot product is just a special example of this inner product. Yeah, very good. Okay, so now in the next section, we're going to talk about one of the use of this inner product, right? So now we have inner products and we have norms on our vector space. So the inner product allow us to essentially measure or assign an angle between two vectors. And the norm allows us to assign a length or a magnitude to our vector. And it doesn't matter what the vectors are, the inner product and the norm will do this for us. So what could we do with angles and length? Okay, so we're going to look at two examples of that. One is orthogonality, and the other is something called the Gram-Schmidt process, right, which is very useful in maths, in science, in computer science. They use that stuff all the time. Okay, so having an inner product allow us to assign an angle between the vectors. So which angle is most important for us? So in particular, it will allow us to tell when two vectors are perpendicular. So the fancy word we're going to use, instead of perpendicular, the fancy word, we're going to use orthogonal. So orthogonal is just another fancy word for perpendicular. So the inner product, yes, it allows us to measure angles between two vectors, but the angle we are after is essentially 90 degrees, right? That's the angle that we are after. So if you remember, if we were dealing with these vectors from high school, these arrows, right? So the angle between these two vectors was this guy, right? It was the smaller of the two angles. The angle that we are after is 90 degrees, right? So the angle we are after is 90 degrees. But again, and you may have encountered this in your high school math, where they told you, okay, if the dot product between these two arrows is 0, then they are perpendicular, right? So now we're dealing with things other than arrows. We're dealing with polynomials, we're dealing with functions, we're dealing with any vector in Rn, n tuples. So what does it mean for a polynomial to be perpendicular to another polynomial? What does it mean for a vector in Rn, an n tuple of numbers, to be perpendicular to another n tuple? Okay, so we'll see about that. So the idea of functions and other abstract vectors being orthogonal or perpendicular is crucial in the study of approximation theory and to construct orthonormal bases. So this is one of the main use of it. When we're going to head towards something called an orthonormal basis. So it's a basis for the vector space, but the vectors now have a special sort of property, right? And we'll unpack what this word orthonormal means in a bit. So first we need to figure out how to measure this sort of angle that I'm talking about. Okay, so we're going to define what this angle is going to be. So again, as usual, V is a vector space over the real numbers. I'm going to define the angle, let's call him theta, and it will be a number between 0 and pi, right? So the angle between any two vectors, u and v, okay? Any two vectors, it doesn't matter what your vectors look like. I'm going to define it to be this equation. So I'm going to define not just, so instead of the angle, it's usually written as cosine the angle, right? So cosine the angle, it's the inner product of the two vectors. And again, it doesn't matter which one, if you do u with v or v with u, right? It doesn't matter which one you put first and which one you put second, you get the same answer. divided by the length of each. Okay, so the inner product of U with V divided by the length of each of them. And you take the inverse cosine of it. So cos inverse that number, and that will give you an angle. That is the angle that we are after. So let's look at an example. So say we are in two-dimensional space, R squared. So our vectors look like pairs of numbers, or you could think of it as simply coordinates, XY coordinate. So the first vector U, we are given it to be 0, 3. The second vector, we are given 4, -1. I want to find what is the angle between U and V. So since we are in Rn, in this case n is 2, we could use the scalar product or the dot product. Okay, so the dot product between these two vectors, remember how you do it? It's the first component here by the first component here. So 0 by 4, right? 0 by 4 plus the second component by the second component. So plus 3 by -1. Okay, and that gives -3. So what we just worked out was this numerator. Okay, now we need to get the length of each vector. So the length of each vector, again, if you're in Rn, is simply Pythagoras' theorem. So it's the square root of x squared plus y squared. In this case, the length of U is 3, and the length of V is root 17. So therefore, I could plug everything into this formula up here, and I get cosine of the angle between them is -3 over 3 by root 17. That simplifies to -1 over root 17. And you get theta equal 1.82. So now remember again, unless I tell you otherwise, your calculator should be in radians mode, right? So it should be, so this is 1.82 radians, not degrees, radians. All right, so are these two vectors orthogonal? Are they perpendicular? The answer is no. If they were perpendicular, then theta here would be 90 degrees or pi over 2, right? If theta is equal to pi over 2, what is cosine pi over 2? Cosine pi over 2 is 0, right? So this guy will be 0 if they were perpendicular. And in order to make the left-hand side of this equation 0, the numerator must be 0. In other words, the inner product must be 0. So what I'm saying is that here we have a way to measure angles between any two abstract vectors. We are searching for when the angle is pi over 2 or 90 degrees. And from the formula, we could figure out what is the necessary and sufficient condition for that to happen. The condition is the inner product must be 0. Inner product must be 0. In order for two vectors to be perpendicular, the inner product must be 0. Okay, so that's stated over here. So now we're going to define what it means for two vectors to be orthogonal or perpendicular. So as usual, V is an inner product space over the real numbers. We say that two vectors, U and V, are orthogonal or perpendicular, however, whichever one you want to use. So it's often denoted by this symbol, right? It's often denoted by this symbol, and this is read as U perpendicular to V. Right? So this is read as U is perpendicular to V. So here's the condition. The inner product between the two vectors is 0. So if I ask you if I give you two vectors, and I ask you, are these two vectors orthogonal or perpendicular? All you have to do is calculate the inner product between them. And whatever inner product you are given, just take the inner product between them. If the answer you get is 0, then yes, orthogonal or perpendicular. If the answer you get is anything other than 0, then no, they are not perpendicular to each other. Okay, so that is what is meant by orthogonal or perpendicular. So now that we have the definition of what it means for two vectors to be perpendicular to each other, we're going to define a set, right? And this set is very important, but it's often a bit confusing when you see it for the first time. It's one of those things where um, you might need a weekend or maybe a weekend plus a holiday to digest what this set really is. Okay, but I'll try my best to explain it. The name of this set is given a very fancy name. It's called the orthogonal complement. Okay, so we're going to find out the orthogonal complement of a set S. So I give you a set. Let me sort of draw a diagram. Here's V, your vector space. Inside of V, I have some set S. Okay, S does not need to be a subspace. Okay, S is just a set. Of course, it could be a subspace. That's fine, but it's just think of it as just some set inside the vector space. Using the set S, I'm going to construct a new set. I'm going to construct a new set, right? And this new set could overlap S. Okay, it doesn't have to be. Well, actually, well, we will see. We have to prove we have to prove some things. And we're going to construct this new set, and I'm going to give it the symbol S and superscript. I'm going to put this perpendicular symbol. Okay, so I'm going to construct this new set. This new set that I drew here in red is what we call the orthogonal complement of S. Okay, so how to find it? What is in this new set? Okay, so it's written like this: S perpendicular. So usually we say the orthogonal complement, or you could say S perpendicular. So it's a set of vectors in V such that those vectors, what is it? So again, now we need to recall our definition from earlier. What does it mean for the inner product of two vectors to be 0? It means they are perpendicular to each other. So it's a set of vectors from V which are perpendicular to every other vector in S. That's what this is saying. So what you have to do is, let's see if I could. So you take a vector in V, right? Take this vector in V. So here's how you construct it. You take this vector in V, and S has many vectors inside of it, right? Let's say S has all these vectors inside of it. If this vector U is perpendicular, so you need to work out what the inner product is between U and every single one of these vectors in S. If U is perpendicular to everything in S, you're going to take U and add it to this set, right? And then you move on to a new vector. So in this way, the orthogonal complement, you are collecting all the vectors in the space that are perpendicular to everything in S. Okay, so that's why it's called the orthogonal complement. It's perpendicular to everything in S. Okay, and we threw all of that in a set. So that is the orthogonal complement. So I know it's sort of like a weird definition, but it's something you just have to think about a bit. We'll do some examples so you see how it works. But yeah, something you have to think about for a while. So that is S perpendicular, or the orthogonal complement, is the set of all vectors in V which are perpendicular to every vector in S. Okay, and we'll see, I think it may be like a assignment question later on that the orthogonal complement is not just a set, it will end up being a subspace. Okay, but that's something you have to prove later on. Okay, so I put over here, given any set, so any set, so now the question is, if I give you any set, could the orthogonal complement ever be the empty set? Or does the orthogonal complement at least contain something in it? Right? And the answer is yes, the orthogonal complement will always contain the zero vector. Okay, so the zero vector is always in the orthogonal complement. No matter what set you give me, the zero vector will always belong to the orthogonal complement. And the reason for that, although we haven't proved it, but you should think about how to prove it. It's a very straightforward one-line proof. The reason for that is because if you take the inner product of any vector with zero, the answer is always the number zero. Okay, if you take the inner product with zero of any vector with zero, it will always be zero. In other words, what this is saying is that zero is perpendicular to everything in the space. The zero vector is perpendicular to everything. Therefore, if you give me any set S, and I'm looking for what are all the vectors perpendicular to every single thing in S, the zero vector always satisfies that property. So the zero vector is always in the orthogonal complement. The question now is, are there more vectors in there? Okay, so are there more vectors in the orthogonal complement? Okay, so let's look at some examples. So there are more examples in the course notes, right? So while you're reading, you'll see some more examples. So the first one is what I just said previously, that the zero vector is orthogonal to every vector in V. Since the inner product of U with the zero vector will always be zero. But you should try to prove it. Okay.
So,
Yeah.
question.
Yeah.
What if S was the empty set?
What if S was the empty set? That's a good question. Let's go back to the definition. The orthogonal complement of a set. So if it is the empty set, is a zero vector. So the orthogonal complement of the empty set will be the zero vector.
Okay, so it's defined to be that.
Actually, would that be the zero vector or the entire set? Every vector, I suspect that's one of those vacuously true sort of statements. But that's a good question. Maybe we say S has a restriction. It's non-empty, right? Because when you usually take in the orthogonal complements, we never really take the set to be empty. Right, but that's a good question. I'll look into it. I'll tell you, it's either going to be just the zero vector or the entire space. Because the proof will go take any element in the empty set, then the inner product between that element and any vector will be zero. So okay. Okay, so I think I just figured it out while talking about it. See, that's why it's good to talk to yourself sometime. Yeah, so the answer is this set here, S, cannot be empty. So what I have here, it cannot be empty. And I know it's not written here because they just say the orthogonal complement of a set. But I'm saying the set S cannot be empty and because it's hidden in the definition. the definition of the orthogonal complement, right, is that it's equal to the set of all vectors which are perpendicular to everything in that set. So in order to do, so my question to you is, if you have to work out the inner product requires how many vectors to put in? It requires two vectors. So to work out the inner product between if I give you a vector v, to work out the inner product between that vector, you need a next vector, right? So you always need another vector. So the orthogonal complement cannot be empty because then you can't do this calculation because the inner product inherently requires two vectors, right? But I suppose they would have put, maybe some books have non-empty sets. Yeah, but that's a good question. I'll look into it just to be sure, but yeah. Any other questions, by the way? No. Okay, well, if you want, you could, yes, and I'll see you have put it in the chat. So if you want, you could type it in the chat or, just unmute your mic and ask me. Yeah, so S, S for us is not empty. Okay. Okay, so what if, so now that I know that the zero vector is perpendicular to every other vector in my space, another way of saying that is that the orthogonal complement of just the zero vector is the entire space. Okay, because the zero vector is perpendicular to everything. Or another way of saying that is that the orthogonal complement of the entire space is the zero vector. So once you understand, remember I told you that the definition of this orthogonal complement is a bit of a weird definition that you have to sit and think about it for a couple minutes. But once you understand what that definition is saying, then these two results will be sort of obvious. Okay, so right now you might be thinking, well, why is the orthogonal complement of 0 V and the orthogonal complement of V 0? So this is something you need to sit and think about. What is this orthogonal complement? And use this fact. In fact, the proof of this, I think, in most textbooks, when they try to prove these two results, they say it follows from the definition of the orthogonal complement, and the result that 0 is perpendicular to everything, that we have these two conditions. Okay, so if you understand why these two results are true, then you understand exactly what this orthogonal complement is. Okay, so if you're looking for the orthogonal complement of the zero vector, it's the entire space. If you're looking for the orthogonal complement of the entire space, it's the zero vector. Okay. But what if we take as a set, not the entire space, so not the zero vector? For example, again, what if we are in R squared, and I give you the set S. So the set S does not need to be finite, by the way. The set that I give you, it doesn't have to be finite. But in this case, let's say it's just these two vectors, 0, 1 and 1, 1. Okay, so that's the set. And I ask you, find for me the orthogonal complement of S. So I want to find S perpendicular. So all of these calculations, regardless of whatever space you are in, for us, we are in R squared, it doesn't matter what space you're in. All these calculations are structured the same way, and they will all boil down to solving a system of equations or solving some simultaneous equation. It always boils down to that. Okay, so let's just write out the definition. What is the orthogonal complement of S? Okay, it's a set of all vectors in R squared. So let's call these vectors xy, such that these vectors must be perpendicular to 0, 1 and perpendicular to 1, 1. We are looking for all vectors perpendicular to everything in S. How many vectors are in S? 2. 1, 2. Okay, so we are looking for vectors that are perpendicular to these two vectors at the same time, by the way. So the catch is in the orthogonal complement, it's not enough to say the vector has to be perpendicular to 0, 1 or 1, 1. No, it has to be perpendicular to both at the same time, right? That's the catch. Okay, so how do we write that? So we are in R squared, so we are allowed to use the usual dot product or scalar product, which means that how to say this vector xy is perpendicular to 0, 1? Well, the dot product between xy and 0, 1 is equal to 0. Okay. And how to say this vector xy is perpendicular to 1, 1? Well, the dot product between xy and 1, 1 is equal to 0. Okay, so this is the condition. So we are searching for all vectors in our squared xy that satisfy these two conditions. Why two conditions? Because we have two vectors in S. Right? So what each of these conditions is going to do is it's going to impose a constraint on this set. And usually the constraints in linear algebra takes the form of linear equations. So what I'm saying is that this first constraint is going to form one equation. This second constraint is going to form a second equation. And of course, you need to solve both equations simultaneously. Okay, so this first constraint, so let me get rid of some of these things. Okay, so that first constraint, if we write it out, we know how to work on the dot product between two vectors. Right, so it's x by 0, which is 0, plus y by 1, which is y. So this first constraint gives me the equation y equals 0. Okay, so I'm very happy. That equation is solved. Now the second constraint gives me x by 1, which is x, and y plus y by 1, which is y. And that is equal to 0. So the second constraint gives me the second equation. And notice the key word here, and. All these constraints must hold at the same time. In other words, you need to solve y equals 0 and x plus y equals 0 simultaneously. Okay, so you all know how to solve it. It's 0. 0 for both of them. So this is just equal to the set of all vectors in R squared such that x is 0 and y is 0. Well, that's just a 0 vector, right? So that's just a 0 vector. So it turns out the orthogonal complement of this set S is just the set with the 0 vector. Remember I said that the orthogonal complement always contains the 0 vector. The question is, does it contain anything more? In this case, no. It's just a 0 vector. Okay? And actually, if you think about it, notice that S, this set S, is a basis for R squared, right? So actually, if you take a basis, you need to think about, if you take as a set the basis, and you're looking for every vector in R squared, or in Rn, or any space, that is perpendicular to everything in a basis, do you always get the 0 vector? So again, something to sit and think about. Okay, so that was in R squared, which is like the easiest example we could look at. So now let's look at a bit more complicated example. And remember to look at the course notes, not the slides. because the slides just have, I'm picking a few examples to go through in class, right? Because I can't go through all 5 or 6 examples. So you need to look at the course notes because it contains a lot more different examples worked out for you. Okay, so let's look at this example. So it's number 5 in the course notes. And V is the space of all linear polynomials defined on this interval, closed interval 0, 1, again with this inner product. Okay, so we saw this inner product already. How do you take the inner product of 2 polynomials? You multiply them together, and then you integrate over the domain. So we are given the domain 0, 1. All right, so let's see what the set S is. In this case, the set is very easy. The set S just contains a single polynomial, P. Okay, where P is defined to be the polynomial 1 minus X. So I'm searching, here's my vector space. Let's say we are in P1. Okay, here's my set S. It contains only 1 point, P, right? S contains only 1 point, P. I'm searching for this set, S perpendicular, or the orthogonal complement of S. I'm searching for every vector or polynomial in the space that is perpendicular to everything in S. So for us, it's very easy because S has just one element, P. So in other words, I'm searching for all other linear polynomials, up to linear polynomials that are perpendicular to this single polynomial P. Okay, so let's see how to write that. So S perpendicular will be the set of all vectors in V. So in this case, V is the space of all. So I shouldn't have said space of all linear polynomials. I should have said P1, right? So linear, because this gives the false impression that it's only linear polynomials and it's not constant, right? So that isn't true. It's P1. It's a set of all polynomials up to linear. So linear and constant, right? So just keep that in mind. I should probably change that. Okay, so we are looking for all vectors in P1 such that these polynomials are perpendicular to everything in S. So I'm calling the vector in S G, right? So it's perpendicular to everything in S. But remember, S only has one element. So to say it's perpendicular to everything in S, I could rewrite that in a very simple way because S only has one element. So I could simply say this is a set of all vectors in P1, right? So in this case, V is equal to P1, all vectors in P1, such that the inner product of those vectors with this specific polynomial P is equal to 0. It's perpendicular only to P. Okay, so how to find this? Well, I need to write down what the vectors in this space V look like. Okay, I essentially now need to evaluate what is this. But I don't know what F is, right? F is just any polynomial in P1. Right, so I'm going to let F equal this general polynomial in P1, A0 plus A1x. So this is a general element or vector in P1. And I'm going to take the inner product of F with this polynomial P and set it equal to 0. Okay, so this guy here is the general form of a vector or a polynomial in P1. And this here is this fixed polynomial P. So remember the inner product, you multiply the two polynomials together and you integrate him from 0 to 1. And in this case, I'm looking for when are they perpendicular. So I set that integral to 0. Okay, so let's evaluate what this integral is. So we're going to expand these two brackets. We get this expression here. Remember, A0 and A1 are unknown constants that I'm trying to find. And so I trust that you all could integrate this. So because it's just a polynomial. So integrated, and plug in the limits from 0 to 1, simplify, and you get 3A0 plus A1 equals 0. Okay, so what does that mean? Actually, if you, even though in this case, the set S just contains a single vector, just one vector in S. So S is as easy as it could be. If you understand how to do this calculation for just one element in S, then you understand how to do it if I give you, for example, 2 elements in S. So if, for example, S had another element, P and Q, or maybe 3 vectors, or maybe 10 vectors in S, the calculation would be the same. Because remember, we saw in our squared, for each element of the set S, you get a constraint on the set. It gives you a constraint. And I told you the constraints in linear algebra show up as equations, linear equations. So if I have one vector in S, how many constraints am I expecting? I'm expecting one constraint. And that one constraint will show up in the form of a linear equation. So this equation is the same as this condition. The constraint that this vector f in my space P1 needs to be perpendicular to P, right? So that this is what this constraint looks like in the form of a linear equation, right? But now you're saying, okay, I have one constraint because I had one vector in my set, so that gave me one linear equation. Do I need a second linear equation because I have two unknowns, A0 and A1. These are unknowns that I need to find, right? In this case, no, you don't always need the same number of unknowns, the same number of equations as you do unknowns. We could solve this equation, even though it's one equation and two unknown. Just solve for any of them, right? So in this case, it's easier to solve for A1, but you could solve for A0. Any one of them, just solve for it. So let's just say I solve for A1. Okay, A1 is equal to minus 3A0. So take this guy across. So I'm going to take this A1 and plug it back into the equation, the general equation of a polynomial in the space. So my orthogonal complement of S is made up of all vectors in P1 such that those vectors look like, so how did I get this? A0 into 1 minus 3x. So I plug in for A1, this equation, A1 equal minus 3A0, and I pull A0 out to the front. Okay, where A0 is any real number. Okay, so in this case, the orthogonal complement of S, yes, it contains the 0 vector. If I set A0 to 0, I will get the 0 vector. The 0 vector is always in the orthogonal complement. But we see it actually contains an infinite number of vectors. Any value of A0 you put, any real number, so pi, 1/2, minus 100, any value of A0 you put generates a new vector in this set. And what is the property of this new vector? If you integrate this guy, or if you calculate the inner product of this vector against P, you will always get it to be 0. right? And you could try this. If you take any vector of this form, a0 into 1 minus 3x, and you integrate it against 1 minus x between 0 and 1, you will always get 0. Okay, so this is the orthogonal complement of s. Okay, so if you had, for example, another polynomial in S, for example, if S was made up of the set with P and the next guy added in Q, then that second polynomial Q will give you a second equation. So then in that case, you will have two equations and two unknowns that you will need to solve. Yeah, uh, so the orthogonal complement, when we first saw it a couple of minutes ago, I sort of hinted that it was something more than a set. I hinted that it was actually a subspace, right? Just like the span. Remember the span of a vector of a set, SPAN, the span of some set S. Remember we saw that the span of a set is not only a set, it's a subspace. In a similar way, if I give you any set S, the orthogonal complement is not only a set, it is a subspace, right? And that's one of the results in this proposition. So this proposition gives us um, uh, some results for how the orthogonal complement behaves and what are some of its properties. So let S and W be subsets of an inner product space. So this means this is the vector space with its inner product. Then the following results hold. So the first one we already saw earlier, the orthogonal complement of the entire space is just the zero vector. And the orthogonal complement of just the zero vector is the entire space. Okay, the second one is what I just said. If W is a non-empty subset of V, then the orthogonal complement of W is a subspace, right? So these orthogonal complements we were taking, not only are they sets, they are subspaces of that set V. Oh, sorry, of that set W. They are subspaces. The third property is saying that S, the set S, so just like the set S is always contained inside of its span, the set S is always contained in the orthogonal complement of its orthogonal complement. So this one is this one you have to, well, you should sit and try to prove these things. And instead of writing the orthogonal complement of the orthogonal complement of S, we write it like this: S with two perpendicular symbols. Okay, so S, so what I'm saying here is don't write S is contained in S perpendicular, right? That is not true. S is not contained in S perpendicular. S is contained in S perpendicular, the orthogonal complement of its orthogonal complement, right? The next property is if S, so when we were taking these orthogonal complements, we said that the set has that S just had to be a set. Okay, so to take the orthogonal complement, S only needs to be a set, and we could construct the orthogonal complement. However, if S is also a subspace of V, so not only a set, if S is also a subspace of V, then the intersection between S and its orthogonal complement is the zero vector. Okay. And the fifth one, so two steps now, if S is a subset of W, then the orthogonal complement of W is contained in the orthogonal complement of S. In other words, to say this, if you have something like A subset of B, what are some operations you all know? Maybe union. Let's say I have two sets, A subset of B, and I'm unioning both sides with another set C. Then I get A union C is contained in B union C, right? B union C. That makes sense, right? So I'm just unioning both sides with C. Notice that the subset relationship did not change. What we are saying here is that if I have two sets, S subset of W, if I take orthogonal complement on both sides, so take orthogonal complements on both sides, then could I write S perpendicular is contained in W perpendicular? In other words, when I take orthogonal complement on both sides, does it preserve the subset relationship? And the answer is no. It switches them around. The W will come first, and then the W perpendicular will be a subset of S perpendicular, right? So it switches them around. Okay, so just something to be aware of, right? And the proof of this is left for you all to figure out, right? Or maybe in your next assignment, I put some of them.
So,
Yeah,
question.
yeah.
If S was a subspace, would V be equal to the direct sum of S and S, the orthogonal complement of S?
Yeah, so that's a good observation. So let me write that out. So what are you talking about there? I think that one they call the projection theorem. I could be wrong on that. Yeah, so what he's saying is um if I give you any vector space V, right? Can you decompose it into and some subspace S? Could you decompose V into S into its direct sum of S and S perpendicular? And the answer is yes. For finite dimensional space, you could do this, right? In this case, S isn't a set, S is a subspace, right? That's the condition, subspace, right? S is a subspace. Yeah, you could do this. So yeah, that's a good observation. Um, for finite dimensional space, yeah, this is true. This is actually a big result. Not a big result, but it's a very useful result in functional analysis. I think it's called the projection theorem or something like that. However, if you step outside of finite dimensional spaces, in order to get this, I think there has to be additional condition on S. Maybe it's a closed subspace. I can't remember. But yeah, this is true for us. Yeah, so that's a good observation. Right, and again, that is something that you all would be able to prove. Yeah, was that the question you were asking? Or did I completely change it?
Oh no, so that was the question.
Okay, yeah. Yeah. I think it's for the projection. Um, actually, yeah, Uh-huh. So, right. So we're going to trusty Wikipedia. Right. So ignore all of this stuff. Yeah, so it's called Hilbert projection theorem. And if you scroll through all of the stuff that you don't need to know, um, um, so the reason why this is so complicated looking here is because they are doing it for any dimensional vector space. So what you're talking about is this here. If so, this proposition, if C, so they are using the letter C, is not only is a subspace, but it needs to be a closed subspace. So whatever that means, you'll see later on. And the vector space, we're calling this vector space H. I mean, sorry, we're calling this vector space V. They are calling their vector space H for this guy Hilbert. Then H is equal to the direct sum of C with C perpendicular. Oh, look, they give you the proof. Okay, cool. Right, so for us, our subspace will be closed, and our vector spaces V will always be Hilbert spaces. These Hilbert spaces are a special type of infinite dimensional vector space, but you could show that any finite dimensional vector space is a Hilbert space. So yeah, right. And this idea comes up a lot in these two things. It's used to prove this result, something called Riesz representation theorem. If you're interested in linear algebra and learning more about this in linear algebra 2, we prove a special case of this Riesz representation theorem for finite dimensional space. Okay, so linear algebra 2 still dealing with finite dimensional space, and um I'm looking for Galerkin orthogonalization. Uh, do we have it here? Or best approximation. So they are calling it a minimizer. Uh, yeah, okay. Well, I'll just tell you. So another consequence of this whole thing is that let's go back to the slide, is that you could get something called a best approximation. Um, yeah, so I'm glad you asked that question. That's a very useful thing to talk about because you'll yeah, so it's good that you asked that question because you're all learning about all these stuff and then you wonder about, well, what is the use of this stuff? So you're learning about all this um orthogonal um complements and projections and inner product and stuff, but like what is all of the use of this stuff? So let me give you a use in a few minutes. So that result that I just wrote here, this guy here, is very useful in many areas of math and computer science, and even in performing computer simulations. And actually, this result here is used to solve differential equations. So you might be thinking, how are they using this to solve differential equations? Okay, let me give you the 2-minute explanation for it. Um, um, say well, I assume everyone here knows what a differential equation is, right? So say you have some sort of differential equation. right? Very complicated, terribly complicated. You don't even know if it have a solution. But let's just assume it have a solution and you can't write it down. The solutions of these differential equations live in vector spaces, right? That's one of the use of linear algebra and functional analysis, which is just linear algebra, but for infinite dimensional spaces. The solution of your differential equations live in these spaces. But what if you are trying to find the solution of your differential equation that lives in some vector space, let's call him V, and it's too complicated to write down. Well, you might say, okay, if you're like a scientist or engineer, you may say, well, I don't need the exact solution. If you could get me, an approximation within 2 or 3 decimal places, I'm very happy. So the idea is in for example, in these sort of things, where we know that we cannot get the exact solution, we get an approximate solution. So here is here's the vector space V, and its dimension is infinite. So this is where the solution is, right? So you have some complicated differential equation, and here is the solution. So that is the solution you're looking for. Let's call him F, right? That is the solution to the complicated differential equation. That is the exact solution. And you're trying to find that, but it's very difficult. So you say, okay, maybe I don't need the exact solution. What could you give me something else? And the answer is yes. What you could do is, instead of working in an infinite dimensional vector space, what if I work in a finite dimensional vector space, right? So, and we know that all finite dimensional vector spaces are essentially Rn. Okay, so I put here it's isomorphic to Rn, right? So there are many vectors in this finite dimensional vector space, right? Which one of these, among all of these vectors in this finite dimensional vector space, which one gives the best approximation of F? Which one is the closest to F? Okay, so we're looking for, maybe it's this guy. Let's call him, I don't know, maybe F tilde or something like that. So we're looking for this approximation in this space, and need the next color. Okay, let's just go with this color. Such that I want to minimize the distance between these two vectors. Okay, so you can't find the actual solution to your differential equation because it's too complicated. So we approximate it in a finite dimensional space. So in the finite dimensional space, how do you find? They call it the best approximation. I think Wikipedia was calling it the minimizer or something, right? And in order to construct or to even show that these things exist, you have to, it basically comes from this thing that I wrote down here, this projection theorem. Yeah, this projection theorem basically comes from this. So this stuff has a lot of application, do just think, yeah, it seems very abstract and stuff, but this stuff is used all the time to solve differential equations. Anytime you see like those fancy computer simulations of like airflow over like a car, or maybe like a simulation of like a rocket taking off, and all of those things, all those computer simulations behind the scenes, they are solving differential equations. They are solving very complicated differential equations. But remember, a computer, they are solving very complicated differential equations. But remember, a computer cannot handle infinite dimensional spaces because a computer only has finite memory, right? So if you want to express this if you want to build this function, you need to express it in terms of something finite. So the computer will there are many numerical methods that use that constructs finite dimensional approximations to like these things. Um, the one that I do work in is something called the Galukian method, or the Galukian finite element method. Is a type of finite element methods. So finite element methods were initially developed by the civil engineers back in the day to solve structural problems, to help them design skyscrapers and bridges and all those things. And today it's expanded from that and is used from everything from modeling heat transfer in uh, uh, whether in computers or transfer of current in developing new transistors or fluid flow to design better, more efficient cars and airplanes. It's used in all of those things, right? So, and in order to understand that, you have to go through all the stuff. Yeah. So I'm glad you asked that question. You get to see some applications of this thing. Okay, so what's on this page? We have, yeah, so back to what back to boring linear algebra, right? Actually, a lot of people who do this course, I talk to them after, say that this course is one of their favorite courses, linear algebra. And I'm always surprised by that because as far as I know, to like mathematicians, linear algebra is very boring. And the reason for that is because in linear algebra, everything is pretty much solved. And in the big brother of it, the one where you do um uh infinite dimensional vector spaces, which is what I keep calling functional analysis, there are many, many problems still open there, still waiting to be solved there. But in linear algebra, everything is really solved. So I'm always surprised when they say they like they like linear algebra. Um, okay, anyway, at least one of us should like this. Okay, so in an inner product space, we have this following very important result, and it might look very familiar to you all. It's something called the Pythagorean theorem. Okay, so it shows up again in inner product spaces. So let V, with this inner product, be an inner product space. If I take two vectors in V, I could say that these two vectors are if these two vectors are orthogonal, then I have this result. The norm of U plus V squared is equal to U squared plus V squared, right? And the proof is left for you to figure out. Why is this called Pythagoras' theorem? So if you draw it, you will see it. You will see why it's called that. So what is the condition? U and V are orthogonal. So let's draw the picture using regular arrows. So if I tell you you have two arrows, let's call this guy U, and and V are perpendicular. Right, U and V are perpendicular. Hopefully I put the arrowhead correct so that I get the correct thing. Okay, yeah. Then what is the vector U plus V? Right, so you'll remember how to do this stuff from physics or the teachers in maths now. Right, so that's supposed to be a straight line. So this vector here is the vector U plus V. Right, U plus V. And of course, this is 90 degrees here. Okay, so what this is saying is that the length, so this part here is saying that the length of this guy squared, which is the hypotenuse, is equal to the length of this guy squared plus the length of this guy squared. So the length of the hypotenuse is equal to the length of the hypotenuse squared is equal to the sum of the squares of the other two sides, right? Which is this guy, Pythagorean theorem, right? So you might be thinking, okay, great. So you proved something that we knew like over 2000 years ago. Well, not really, because I never said that we are working in R squared, right? This is true for any inner product space, right? So we could be working with polynomials or functions or matrices with other types of inner products, and this is true, right? So that's the use of this. And from that guide, you can use to prove something called the Cauchy-Schwarz inequality that I think you may have met in first year course, maybe in when you were studying complex numbers, maybe. And so from the Pythagorean theorem, you can prove this guy. And it says let V be an inner product space over the real numbers. Then for any two vectors, remember the inner product of U with V is a number, right? This is a number, but this number could be negative, by the way. So what this is saying is that the modulus of this number is less than or equal than the length of U multiplied by the length of V. So it's less than or equal. When do you get it equal? You get it equal, so you get the equality if and only if the two vectors U and V are linearly dependent. Okay, so if these two vectors are linearly dependent, you get the strict equality here. You get a nice equality. If you don't know whether or not they are dependent or independent, if you don't know about that, then you need to put less than or equal. Okay, and this guy is called Cauchy-Schwarz inequality. And again, you might be saying, okay, well, we proved this in year one. So great, we proved something here that I knew from last year. Well, not quite again, because in year one, in the first year course where I assume you met this, you all may have done it for complex numbers, right? Complex numbers are vectors. Are we talking about complex numbers here? No, we just said V be an inner product space over R. So this works for more things than complex numbers, not only complex numbers, any inner product space. Okay, this will work. So this is called Cauchy-Schwarz inequality. Very important. And from Cauchy-Schwarz inequality, and you see you have to, all of these are left as an exercise for you to prove. But if you all are reading a textbook, like I assume everyone here is reading a textbook or following along with some book, all of these results you will meet in that textbook because any linear algebra textbook have these results proven in because these results are crucial for many other proofs later on. Okay, so from the Cauchy-Schwarz inequality, you could prove this guy, the triangle inequality. Now, again, you may have met this in your first year courses where you study complex numbers, but it holds not only for complex numbers, it holds for any inner product space. Okay, so it holds for any inner product space. So what is the triangle inequality? It says that the length of U plus V is less than or equal to the length of U plus the length of V. And again, you have equality here. When is this equal? You have equality if and only if these two vectors are linearly dependent. Right? And why is it called triangle inequality? Let's say you have 3 points, right? So this first point is your home. This point here is your school. And this point here is food. So instead of going from home straight to school, you decide, no, you want to. So instead of going from home to school, you say, no, I want to go pick up some food first. And let's just say, for the sake of this diagram, that the food is out of the way. So it's not on the way to school. So you have to go to get the food first, and then the food to school. Okay, so which path is longer? The blue part or the green part? The blue part is longer, right? So the blue part is this guy, right? So let me put some letters to it now, so you'll see. So this guy here, let's call this vector u. Home to food is u. Then food to school is v. And home straight to school, like what your parents assume that you're doing, is u straight to u plus v. Right? So this is saying that, let's get rid of this. This is saying that the length of the green part, u plus v, that distance is less than or equal to the distance u plus the distance, or the length, I should say, of v, right? So that's what the triangle inequality is saying. And you see, if you draw the picture, you got a triangle. That's why it's called triangle inequality. Okay. And so we have orthonormal basis. What comes after this one? Orthonormal, and then Gram-Schmidt. Yeah. Okay, so we won't start orthonormal basis yet. So we'll stop there for today. Okay, so I see we have a question. Being on the path between home and school corresponds to, yeah. So so according to this diagram here, the question was, so in this diagram I said, for the sake of me getting a triangle, what if the food was not on the way between your home and school? So I drew it out of the way, right? So the question is, if the food was on the way to school, so along the green arrow, does that mean that u and v are linearly dependent? And the answer is yes. So when you get equality for the triangle inequality, when you get an equal sign between them, yes, it corresponds to everything along the green arrow, right? Then there's no detour. You go straight, right? Yeah. Okay, so we'll stop there for today. Are there any questions?